All right. Got the ecology crew filtering in.
All right, so I think we can get started.
Yeah.
Everybody, welcome. We're going to be hearing from Jacob Schultz. This is essentially his master's project, 501 project, what we call it. He's going to talk about a topic that's dear to me, which is at the interface of spatial statistics and ecology. And the floor is yours.
Thank you. It's good to see you all here. Bayesians that should be studying for their exam, Daniel, ecology people. My mom actually was able to come down from Petersburg, Alaska. She just happened to be in town with the newly elected mayor of Petersburg, Mark, her boyfriend. Yeah, so anyways, I wanted to start out talking about the story of this project a little bit because it has to do a little bit with the outline of how I'm going to present it. So this time last year, actually it was over Thanksgiving break, I shot an email to Daniel for the first time and asking about spatial statistics and ecology. I didn't really know what I wanted to do. I just knew that I would like to go back to Alaska and possibly model fish and game for Department of Fish and Game, and I didn't know the statistics involved. And so I knew that Daniel, I'd heard that he had done something similar and basically reached out and he sent me a whole bunch of papers, possible 501 papers. And these things were a wide range. There was things like Bayesian model selection and spatial autoregression, all these different topics. And I was using that as just this idea, as basically just to get an idea of the type of topics that are out there in spatial statistics and ecology, but nothing was really sticking for a 501. And then he gave me an early draft of this Gelfand and Schroeder paper, which I'm going to be talking to you about today. And that one fit the 501. It felt better. It was, but the issue was I was having some issues interpreting the long, drawn-out philosophical arguments that he was making, differentiating the types of data and why one model is better here and worse here. And I realized I needed a basis in spatial statistics, which is when Daniel just lent me a copy of this book, which is written by Banerjee, who is actually one of Gelfand's previous students. And Gelfand is the third author here, so it's a small world. And so that's actually where we're going to start the talk. We're going to start going through the three main types of data that arises in spatial statistics. Because without this, you really won't be able to understand anything that Gelfand is trying to get across. These distinctions are fundamental to the rest of the argument. Then we're going to talk about presence-absence versus presence-only data. These are two different types of data that are commonly collected in ecological studies. So the first part is just spatial statistics in general. Now we're narrowing it down to ecological statistics. And then we're going to talk about preferential sampling in geostatistical modeling, which is this cool way of adjusting for maybe oversampled areas that you're more likely to see the species. We have to get a really good basis in this concept because this is the framework under which we can fuse presence-absence and presence-only data. So the idea is you have both data sets. You use different models for each of them. Is there a way to get a model that you can employ both data sets at the same time? So that's the goal. So let's start out talking about point level, sometimes called point reference data. The idea is that you have this fixed domain of interest. I'll call it D. Usually two-dimensional. Three-dimensional would be like maybe you're modeling water columns in the oceans. The depth actually matters. But for the rest of this talk, I'm just going to be talking in terms of 2D, just for simplicity's sake. The idea is that you're going to measure some set of points within that domain. You're going to select those points. You're going to go there and you're going to measure some response. And the goal is to fit a continuous response surface over that domain of interest. And so then, even at points that you haven't sampled, you could kind of predict where you think the response should be. So this is what the data, your raw data would look like if you went and did a study like this. We can look at, this is called a drop line scatter plot. The idea is that you have like your longitude and latitude of the points that you gathered, and then the magnitude of these vectors are the responses that you're measuring. You could also do an interpolated level curve. That's what this is. It's essentially, I kind of think of it like a linear spline, but in 2 dimensions. So that actually, if you wanted to, you could use that as a prediction surface, right? You could, because that allows you to see some kind of predicted response in between the points that you sampled. But there's some issues there because the surface, it's obviously not differentiable, right? It's not smooth. It's got all these points and edges. It also, the most obvious thing that's wrong with it to me is that there's no way to quantify your uncertainty. So if you make a prediction at a spot you didn't sample, there's no way to create a confidence interval or a credible interval about your prediction, which is statistically irresponsible. So this is the model that we're going. So the idea is that we would like to use a regression method, where we're going to assume a parameterized model somewhere, and then that way we can jump into confidence intervals or credible intervals. So that's what we're going to do here in this method called Kriging. It was named after D.G. Krieg, who is a South African mineral engineer, and it's a regression technique that employs a Gaussian process. And so I'm actually going to skip over a lot of the nice, elegant theory of Gaussian processes. Sorry, Bruno. Really, for now, we're just going to say that the data is modeled as a multivariable normal with a fairly fancy covariance matrix, and we're going to get into that in a second. But first, I want to sell you on why this is a cool approach. These are the results that you'll end up with. Here, you can't read them, but there's the points that we sampled, and then the number associated with it is the response that we measured. And we see these areas where we have low values and it's blue, and these areas of high values and it's red. And you have this surface that kind of hovers over the area of interest. And there's this important piece there's an important argument that things that are close together will probably behave similarly to each other. So that's what we mean by spatially dependent. And so we see that we have clumps of small numbers and clumps of big numbers. And so that means that we can model our data as actually correlated with each other, not as IID draws. That's the big change between modeling in regression typically and then using a Gaussian process. Okay, here's another really good selling point. We also have a standard error surface we can generate across the whole domain of interest. And this standard error surface will allow us to create confidence intervals for any predictions that we make. And, or actually confidence surfaces. You can imagine a surface down below and a surface up above. And between those two surfaces, at any given point, we have a 95% confidence interval, for example. And you'll notice we have these little white dots here in the standard error. Those are like really hard local minima of standard error, and those represent the points that we actually measured, because we're pretty darn sure that those responses are true, right? So we're at a very low standard error at those points. So yeah, here's the motivation. Objects that are spatially close might act similarly. So habitat suitability is locally constant. If we look at the small enough scale, then the difference between this place and this place is pretty much the same. That's the assumption we're trying to model. And so here is the basic layout of how we would model our data. Our data is multivariable normal. We can use no covariates or with covariates, because of course this is the more general case. This is what I'm going to be carrying on through the lecture, is we're having covariates. And then here's a multivariable normal. The errors here are multivariable normal with this sigma matrix. And that sigma matrix is generated according to some function C that is what we call a stationary isotropic covariance function. And stationary and isotropy are two different qualities that each mean their own thing on their own, but together, basically what that means is that the covariance between any two points is purely determined by the distance between those points. So it doesn't matter what their orientation is, and it doesn't matter where on the plane they lie. If they're the same distance apart, they have the same covariance function evaluation. And covariance functions with that property end up looking like this, where we have this sigma squared parameter, and this row of phi and d is our correlation function, which is chosen. So for example, this could be a matern. This covariance function could be a matern, and then you would have some expression here in terms of these values. And then we have this other third value, tau. Now, tau is called the nugget effect. We can kind of think of that as random noise that we build into the model. Notice the closed bracket there. It could be 0. It's an optional thing we can include into the model to allow it to be a little bit more flexible. And what that essentially does is it allows you to build in any uncertainty that you might have about your measuring, your measurement error. So if you're sure that you don't have any measurement error, you can set tau to be 0. And it also kind of, another interpretation is that it helps you model these surfaces on scales that are smaller than the distance between the two closest points. So it allows you to have a little bit more fine prediction. The phi is, just think of it as an extra parameter you're going to have to optimize for, but it's called a decay parameter. So here's a slide where I'm reaching out to the Stat 564 students and those who have taken it, trying to link that course with what I'm talking about here. You just saw this matrix representation of multiple linear regression probably 4 weeks ago, something like that. The main takeaway is that if you assume that your errors on your response are IID, then that means that your errors are multivariable normal with this diagonal matrix as the covariance matrix. And that implies your data is distributed this way. So let's take a look at this covariance matrix. We have the diagonals being identical. That is the identical part of the IID. And the fact that the off diagonals are 0, that is the independence coming through. So here is what the equivalent would look like for Kriging. So this is me just taking that covariance function from back here, plugging it into its matrix form. And so here we have this assumption that the epsilons are distributed multivariable normal, and then that implies this. So really, the idea here is that this off diagonal will allow you to measure the covariance between the first point and the second point, right? It's that expression. And then this d is the distance between the first point and the second point. And so just as a convention, I decided to keep this d21 and d12, but because reality is a metric space, right? This is equal to this. Okay, so you can swap those indices. Cool. So, okay, this is a very important note. If we're able to explain all of the variation in the response using these predictors, then we would expect the errors to be just measurement error, right? If we knew everything about the system. And so the ideal is actually to use a multiple regression model. But the spatial statistics equivalent, the Kriging model, allows us to take things that we can't explain through the covariance structure and explain it spatially. So this is used to model residual spatial dependence, which I know you can't read that, so that's basically what that says. So here's an example of a pretty surface that you would fit to data Kriging surface. You might have seen this on my poster. Yeah, so you can see that it's probably fairly easy to differentiate. You can do all kinds of nice things with this beautiful surface. You can also have these two surfaces above and below it to capture your confidence. Here's another example contrasting this that linear spline approach and then a Kriging approach. So certainly more visually appealing, which also helps, right? Okay, so let's talk about aerial data now. So that was the first type of data, was point level data. Let's talk about aerial data. So the idea with aerial data is that we're going to partition D into a finite set of subsets, and we'll call those aerial units. And then at each aerial unit, we're going to measure a response Y, and we might measure covariance as well at each of those. And then you could plot those responses in a color graph like this. So I'll explain what these are. This one right here is a binary land use classification for a certain part of Madagascar. So whether or not it's forested or not forested, it all looks black. But there's some gray in there, I swear. And then this is SAT scores from 1999, verbal SAT scores, black being worst, white being the best. So these are examples of aerial data. A common use case here is censoring sensitive information. For example, the SAT scores, right? We don't want to publish individual SAT scores, but we could aggregate at the school level and the county level and at the state level and publish those ethically. And it also allows us to summarize data with vague location values. So, for example, the students, it doesn't really matter to us where they happen to be exactly. We just want to know where they went to school, right? And that is something that we can measure, is where they went to school. So we have a vague location, and we have sensitive information. Therefore, we should probably be modeling at the aerial level. So that's where it's useful. Of course, the drawback is that you're going to be generalizing over the whole aerial unit the one response that you collect. So if your aerial units are large, like for example, California's large, and we know that the state of Jefferson gets salty about certain things. You know, they don't like to be lumped in with the rest of California with a lot of these responses. So that would be an example of a drawback. We're generalizing sometimes outside of appropriateness. Yeah.
Yeah, so do you mean that the SAT results are actually better in the Midwest
Yes.
than they are on the coast?
Yes.
Okay.
Yeah.
What would be the covariate that would help to explain that?
I would think socioeconomic factors would be the first thing that pops into my head.
Going to college and things like that.
Yeah, I mean,
It has to do with more who's taking the exam. The people,
oh yeah, that's a good point. Yeah, yeah, maybe. Sorry, go ahead. Yeah.
the people taking the exam in some of the areas include a large number of people who may or may not be going on to college, whereas in the Midwest, it's more restricted.
Yeah, like maybe if you're in California, you're in a...
Most of the Midwest, if you're probably taking the ACT if you're serious. And if you're going to a state school. So you'd only take the SAT if you're going to a private school. And so the people taking, well, that's not everybody, but they're more likely to be going to a private school here. And so you're going to be doing better.
Okay, interesting.
Yeah, many things at play there.
Has nothing to do with
Yeah, yeah,
Couldn't resist to ask.
yeah.
Probably not much.
Yeah, it might also be just a social norm that in richer places along the coast, people go to college, so even the dummies take the SAT, right? Because that's just the social norm. Whereas like if you're in the Midwest, you have a lot of blue collar options, and you only take the SAT if you actually have, so that might be another. So, okay, so that is the data. That's what the raw data looks like. Yep.
Is there some standard way of generalizing across an area to one unit, or does it depend on what you're measuring?
It's tough. So this is, I use this binning intentionally because this is a binning problem. And any binning problem, where you set the boundaries of the bins has a massive effect on what the outcome looks like. If you ever try to make a histogram in R and you try to deal with that parameter, you can make a normal distribution look like uniform if you set that fine enough, right? So where you draw these boundaries has a massive effect on any conclusions you might draw from it. So it's always right for criticism if you see generalized results like this. Cool. So this is what the raw data looks like, right? We haven't done anything statistically to it yet. We've just represented the responses. How do we do statistics on it? Most of the statistical techniques used on aerial data are smoothing techniques. The idea here being that, again, we might have spatial dependence. Things that are close to each other may behave similarly to each other. So for example, so the idea is that you could take aerial units and you could kind of average its value with its neighbor's value and kind of inform the response that we're looking at by its neighbors. And that's kind of based on this assumption of spatial dependence. And you can think of that as taking a very jagged histogram thing and kind of evening it out a little bit. And it really helps being able to see the general trends. So here, this is student infant death syndrome rates before and after a SAR smoothing. So this is a particular smoothing technique. Here, it's really hard to tell what's going on. And then we look at after the smoothing technique, and we see that as you go further east, generally you get a worse situation. You get more sudden infant death rates. So this would be like Appalachia, and this would be more urban. And then we have some coastal things happening here too. But you wouldn't be able to see that pattern if you didn't smooth. So I'm just going to talk a little bit about kind of what the flow of fitting this model looks like, but we're going to leave it very quickly because it doesn't have to do with Kelvin and Schroeder. So one of the cool hallmarks of these kind of models is you have to define something called an adjacency matrix. And that basically tells you how each of the aerial units, how close it is to the other aerial units by some metric. And so a first example might be assign 1 if and only if the 2 aerial units are touching. So it's like, okay, they actually are neighbors, they share a border, and it's 0 otherwise. Another thing you could do is you could define centroids. You can find the centroid of each of the aerial units, and then you could take the distance, which is harder than you might think on a globe. You could take the distance between those and set that as the entry of your adjacency matrix. So that's another way you could do it. There's many other ways, especially if you have like a regular grid, you can get kind of creative with it. And then once you assign all that, you proceed similarly to autoregression and time series, if you're familiar with any of that. So the issue here is that in time series, you have one direction, and you're clear where front and back is. But in spatial statistics, it kind of goes out in all directions. And so that's why defining this adjacency matrix is more of a challenge in spatial statistics versus time series.
Couldn't you apply things like creating near, though, the same way?
I think so.
And couldn't you apply autoregression in
the other data.
Yeah, I think so. I haven't looked into that. Yeah. I mean, especially since a lot of Bayesian techniques are going to be discretizing anyways. So a lot of times the models you end up using for kriging end up kind of being modeled at the areal level anyways. So yeah, this is just the very basics. Just like, yeah, but you can get more creative with it. Cool. So this is, if you saw an earlier draft of my paper, you might have seen I've spelled this word like 8 different ways. Well, I'm actually justified in 2 of them because the first 2, aerial and aerial, those actually mean similar but different things. And so I thought this would be a useful piece of trivia to throw in. This is aerial data. This is what we've been talking about so far. We're showing Oregon as a union of areas, okay? And then this is aerial data, which is aerial map, right? Which has the root word air, which is a view from above, okay? So those are 2 different maps that show similar information, but different for sure, and they're spelled certainly way different. But neither of them are spelled like the mermaid. Okay, cool.
But you had that third one on your prior chart.
Oh, did I? No.
Go back.
Oh, I'm not going back. You're not going to prove it. No, there's no way. Okay. I'm not taking that bait. All right. So point pattern data. This is the third type. And this is important because this comes up a lot in the Gelfinite-Schroeder. The idea here is that the domain itself is random. We have a domain of interest, but within that, we have a certain amount of points that are going to be realized, and we're kind of assuming that they're realized in terms of an intensity function that we'll talk about later. So the common example of this would be like plant studies. So this is like maybe an island. It's maybe an island, and you're going to go out there and you're going to measure where all the trees are at. And then, okay, so a marked point pattern is when we additionally measure other covariates. For example, this, or responses. So in this map, we actually have circles and triangles that you can't see, and these are 2 different species of trees. So that's a marked point process. Here's another marked point process where the radius of each circle is proportional to the radius of a tree that was measured at each of those points. So not only have the locations of the instances, we also have some information associated with it.
Jacob, just to make something clear, what you're saying is that the points are random. Where
Yep.
something occurs, where the event occurs, is
Yeah.
what's random. The location is random.
Yes, the location itself is random. So remember,
Probably of occurring, it is also spatial though.
Yeah.
It'll be nearby ones may have a different
yeah,
intensity than.
exactly. We could have clumping effects. Yeah, we might have.
Like nothing.
Yes, exactly. Cool, and we'll talk about that in a second. So yeah, that's actually what we're talking about right now. The first modeling concern you should be asking is there a spatial dependence? So clustering or anti-clustering would be an example. So this is, I couldn't find good enough examples, so this is hand-drawn. In this example, we have a point process that was realized over our domain of interest, and we have these clusters. And so that shows that we might actually have an intensity surface that's responsible for these realizations that is like kind of high over here and high over here, but maybe low over here. So there's some kind of spatial dependence happening. I found a really cool article that said this really well. This is from a UW News article. It says, additionally, they found that morels mushrooms, those tasty ones, right? They found that morels clustered in groups across burn areas, meaning that if finding one mushroom, the likelihood of finding more increased within 10 to 23 feet of the first. So if I find one mushroom between 10 and 23 feet of that first one, I should expect to see more, right? That's what that says. So that's an example. Well, this is an activity that I came up with that if we have time at the end, we'll do it. It's fun, but I don't know if we'll have time. So the thing is, we have the eyeball method. Is there clustering or no? It's not easy. That's kind of the thesis of the activity. We can use some non-parametric methods such as Geary's C and Morgan's I. I'm not going to go into those, but there's just some metrics that we can use to see how well these things are clumping to avoid that eyeball method. Not very defendable. What we're mostly interested in, though, is modeling that intensity function that I've alluded to. If we were to sample that point process again, if we were to come back after the next burn and look for morels, where should we look? Where should we expect to see another point process be focused? So we wouldn't want to look over here. We would want to look over here. And so we want to build that intensity surface to help us predict. Cool. So the models that we're going to be using to create that surface we're going to be using Poisson processes and Cox processes. That's what we're going to talk about here. So the notation here is that S is going to be the set of those points that gets realized within D. That's a random realization of the point pattern in D. And then, okay, my spacing's a little bit weird, but this lambda of S is that intensity surface that we're trying to model. Okay, so you see it's a function of S. This S is a vector describing the point. And so what if that intensity surface was constant over D? This is called a homogeneous Poisson process, and that means that lambda S equals some constant lambda for every point in D. And so the example here is your classic one you would see in undergrad probability courses when you first see a Poisson distribution. The example here, the field mice are distributed over a field with an average density of 19 burrows per acre. How many burrows would we expect to see in a 4.2 acre plot? So intuitively, you would just multiply those numbers, right? And that is exactly what we do for the expected number of occurrences within a certain area I'm calling A. So that area A is that 4.2 acre plot, and then around that vertical bars means it's the area of A. So we'd plug in 4.2 there, and then that 19 is our average lambda. So that's nice, but the issue there is that we're assuming a uniform intensity, and that's not very descriptive, especially if there's spatial dependence. So what we could do is we could build a non-homogeneous Poisson process where we're allowing this function to change as we move over the landscape according to some vector of covariates here. But what's even better is what if we could take into account spatial dependence? So what we're doing here is we're using a log Gaussian Cox process where we're starting with a non-homogeneous Poisson process, but then we're adding a Gaussian process there to account for spatial dependence in the same way that we would in a Kriging model. And so that allows us to get that idea that things that are close to each other behave similarly to each other, that Morel idea. So this is the model you would use for Morels. Then you can find the expected number of points think of it as the average intensity over A times the area of A itself, right? That's kind of intuitive. That's really what we're doing. That's really what we're doing up here. But we have to use an integral because it's not a constant intensity over the area. So that's what this integral is doing, is it's kind of finding the sum of the intensity over A, and then it's dividing it by the area of A, and think of that as the average intensity. Multiply that by the size of A, and you just get this. And we're defining it for notation's sake as lambda of the set A. Okay? That notation will come up later.
Just one thing here, it's given epsilon that indeed this is like that.
Oh yes, given epsilon.
Right.
Yes.
Lambda is right.
Yes, exactly. Yep. Cool. So let's talk now. We've gone through the three types of data. So we've gone over the first few chapters of this book. And now we're getting into the ecological specifics, which pop up in the paper. So now we're talking about presence-absence versus presence-only data. So the goal for both of these types of data is to collect presence or absence at a location and possibly some covariate data for use in spatial models. So presence-absence data, you find a set number of points that you're going to go visit, and you measure presence-absence at each location. Was the species there or not? And these locations are often planned, and this is best modeled by trying to fit a surface that describes the probability of presence continuously over D. That's the goal. We're going to talk about that in a second. So the big takeaway is that this is point-level data. And then presence-only data, these are a list of locations where sightings of that species has occurred. And often this is opportunistically. If you're a field biologist, you're out studying birds and you happen to see a mule deer, you tell your buddy, oh, I saw a mule deer. He says, oh, good, I'll mark where that happened, right? That would be presence-only data. It might be opportunistically gathered, but it doesn't carry information about the visited areas with no sightings, right? That person isn't saying, oh, I went here, went here, went here, and didn't see mule deer, but then I saw one here, right? So it carries a little bit less information. And this is best modeled as a point process. We have two different types of data happening. This is what makes the fusion problem hard. And so let's talk specifically about how to model these things. We're talking about presence-only data because it's a little bit easier to wrap your head around. We're just going to be fitting an intensity surface. This is almost a copy-paste of those last few slides I was showing you about. although I should say that we can do some model selection here, if the Gaussian process parameters are insignificant, you'd be well served by dropping them and using a non-homogeneous Poisson process, or even just a Poisson process. So it's not required that you use log Gaussian Cox. And just as before, you can find your expected number given epsilon for any area. But now I'm going to talk a little bit deeper into the interpretation. Really what we're trying to get at is a probability of presence, a coherent probability of presence interpretation. So what's the best we can get out of this data? What we could do is we could take that intensity surface that we fit using the data, and we could divide it by basically integrating that intensity over the entire domain of interest. And that will normalize that surface down so that it integrates to 1, right? And if it integrates to 1, we now have a continuous density function. That's all that this expression is showing. So now we have a density, but how do we interpret it? That's kind of weird. The interpretation is if you integrate this density over some area A, that gives the probability of occurrences in A, the percentage of the occurrences that would happen in A relative to the total amount of occurrences that would happen in D. So for example, if I picked an A and I integrated this density over A and I got 0.5, I could conclude that I think that 50% of the occurrences that happen totally in this area will happen in that subset. That's the takeaway here. So it's really iffy dealing with this probability of presence interpretation though, because it's totally dependent on, so everything's relative to that original D, that original domain of interest. And so we can't generalize outside D, of course. I mean, we might be able to extend that surface out kind of irresponsibly and make some kind of argument, but really, if we're going by the book, we can't generalize this outside of D. But more importantly, this all assumes a perfect census of D, right? So our estimation of the total number of occurrences that are going to happen in D is based on this assumption that we fully saw the point process in this area. So if you imagine those pictures I put up with all the dots, the idea is that you went through and you actually censused every single point in that domain of interest. And that's a bad assumption that we can work. We'll talk about that later. Oh, and then another issue here is that relative probabilities can only be found in terms of areas, right? Because what do you get when you evaluate a density at a single point, right? What's the probability of me drawing a 0 from a standard normal? 0, right? It's 0 probability. The only way you can calculate probability is by integrating, by getting some kind of function of a CDF. And so we have to integrate this density in order to have a probability of presence. So for presence-absence data, we should be using some kind of kriging somewhere, because this is point-level data. But the issue is that the response that we're dealing with is binary. It's not continuous. So that prediction surface we've been thinking of with kriging, it is a continuous surface that can range anywhere from, well, it actually could be negative if you wanted it to, but it can be anywhere in the reals. We want to constrain that surface to be between 0 and 1 somehow. What that means is that we have a categorical data analysis problem. And just like any other categorical data analysis problem, you fix it by applying some kind of fancy link function that would serve your purposes. So you might use a logistic regression, logit link here. Gelfand and Schroeder use a probit link, which I think is pretty elegant, and that's what we're going to be using for the rest of this presentation. And so what we do is we're actually modeling it as a latent Gaussian process. So think of this Z as a surface that is unconstrained. It can move anywhere up and down in the reals. This is the geostatistical model that we desire, but the way that we link it with the data Y is through this chain of equalities. And basically what this does is you're taking this expression, you're plugging it into the CDF of a standard normal distribution. And then this CDF will therefore map this function into the range of 0 to 1. Okay, so that allows us to model probabilities of presences because we're now mapping it to the range of 0 to 1. And the idea is that whenever this Z is positive, that is an indication that we have a 1 as the response. Note here, though, that there's a slight difference in notation. This epsilon is a different font than this epsilon. This is the epsilon. It's a Gaussian process that doesn't have the nugget effect. And the reason for that is when you go through this process, this is a deeper derivation that I'm showing, you end up taking an expectation. And the expectation of that nugget effect is 0, because it's just a random noise term. And so just like in a prediction function you might produce in regression where you don't take into account that error term drops out in this expression as well. And so the nice thing about interpreting probability of presence with presence-absence data is that the resulting function, the resulting regression can be plugged into that normal CDF, and then we actually have this y hat, which is it's a surface that lives in 0 to 1 and describes probability of presence at any point continuously along D. So this is actually kind of like the gold standard. We can evaluate a single point and say, what's the probability of seeing the species here versus the aerial scale from the previous type. So I want to make a note here. So far we haven't seen the nugget being used. Where does that nugget come in? Well, that tau hat, that fitted nugget, it plays a role. That's how we kind of quantify a certain source of uncertainty, that measurement error. And so it comes into effect when we're generating confidence intervals or confidence surfaces. So you don't see it here, but if you wanted to create those confidence surfaces, it's fundamental for those, assuming you haven't dropped the nugget from your model already. So here's, just to make sure we're all on the same page about the differences, we model presence-only data as a point pattern. So the locations are random. We can only interpret probability of presence at the areal level by integrating. And it requires that assumption of a census study area. And then with presence-absence, all of the locations in D are considered, all the locations are fixed, and the response is the random thing. So you're going to pick the spots that you're going to, and then you're going to measure either a 1 or 0. So that response is the random thing. The locations are fixed. And we can interpret probability of presence at every single point continuously, and it doesn't assume a census. It's impossible to census this, right? Because you would need to census every single point along that continuous domain. Uncountable. So the central problem of Gelfand and Schroeder, again, is what if we had both of these data sets and wanted to use them both at once? So we need a new tool to tackle this problem called preferential sampling. So what is preferential sampling? Ideally, we would want sampling effort over D to be uniform so that we can get, we aren't biasing our results. But that isn't always the case. Here's some examples of how preferential sampling could arise in ecological studies. Maybe the data was collected opportunistically. So yeah, a field biologist records a sighting during an unrelated activity. You can't uniformly sample opportunistically. Maybe access to locations are limited. This is the main factor for preferential sampling, in my opinion, is it's just hard to access the top of a mountain or a meadow that's way off the road system. So that might be another issue with preferential sampling. In these two examples, it's hard to see how that would bias your results. Does this mean you're oversampling presences or undersampling presences? It's not obvious where that bias would lie. So that's especially insidious. We don't really know how to deal with that very well without preferential sampling modeling. Here's another example that comes up a lot. Researchers collect data in areas that they're more likely to see the species. And it sounds kind of silly if you're a statistician and you're in all this probability theory, but if the protocol for a study isn't made clear, a field biologist out on their own might say, well, I want to spend my time doing useful things. I want to go get data. The more data, the better. So I'm going to go to the spot where the species is at. That's the best use of my time. So unless they're assigned the location to begin with, when they're given free rein, they might end up in spots that are causing us to oversample presences. So here, this third example positively biases the occupancy estimates, and assuming the researchers are good at targeting them, right? That assumption is carried through. But the alternate wording here is that presences are oversampled, and that's the kind of wording I'm going to be using from now on. Just think of this as presences are oversampled. Here, we don't know if presences are over or undersampled. So yeah, here's some notes. These scenarios are common in ecological research, and this is very important. Just because you're not clever enough to see any sources of preferential sampling doesn't mean there doesn't exist something that is causing preferential sampling in your design. So you might not be able to be clever enough to see that this is an issue. So if you said, oh, we were really good, I made sure that the protocol was good, we don't have preferential sampling, and you moved on, you might run into some issues, especially if there's not very good compliance with the field biologists. So ideally, what you would want to do is you'd want to be able to quantify the amount of preferential sampling in your data and be able to adjust for that in your regression model. And what would be even better is if that quantified measure was a parameter that we could get confidence intervals on, and we can see if that parameter is significant or not, and determine, we can formally test if we have preferential sampling using that procedure. And that's exactly what we're going to be doing. So for this, I'm going to be working under this model for the rest of the talk. It's just an example I cooked up. Here we're doing a hypothetical Himalayan blackberry study. And the line that you see is a pathway through the forest, you can imagine. And the points that you see are sampled areas in our presence-absence study. And the dark is a presence and the light is an absence. Now, a few things to know about the Himalayan blackberry. It's an invasive species. It's not native to Oregon. And let's assume Oregon. It's not native to Oregon. It's that species you see along I-5. It's in your backyard. It's everywhere. Some things to know about it. It spreads through the excrement of omnivores. That's one way it spreads. And so we might imagine that omnivores, like bears or all those other things, foxes, could be using the same trail that we're sampling at. So we might have a lot of seeds being dispersed across there. And another thing that's, so as Kat would say, that's a high propagule pressure along that path. Another thing to know about this species is that it takes hold especially well in disturbed ground. And we can assume that a trail that's used a lot might have disturbed ground, especially along the edges. It's being torn up a lot. So that's a really good place for that species to grow. So knowing these two things, we should be tipped off that we have preferential sampling happening. And we can kind of know in what direction the preferential sampling is probably occurring, because we're sampling along this road, and knowing those ecological details about this species, we know that this is the best spot in D, in the whole area of study, that this species could be growing. So we probably oversampled presences here. The implication being that if we fit a Kriging model to it, that probability of presence surface will be inflated artificially. It'll be a little bit too high than it should be. So that's what we're going to try to account for. And the way we account for that is we build in what's called a shared process. So this Z right here is the Kriging surface that we're used to, but it has this extra term added into the mean structure. Where does that come from? It comes from this, which is a point process model for the points that we sampled. So the main thing with preferential sampling is that instead of assuming that the points that we're sampling are fixed and that the responses are random, we're now assuming that both the locations and the responses are random. And we're using this point process model to model that point process realization, the locations as random events. So this equation is exactly what we would see in the previous slides for a point process, but it's in terms of these points. And there's a slight difference in notation because I'm using an eta for that Gaussian process term. So this is the spatial dependence component in this model. This spatial dependence is built in also to this Kriging surface, and it's being multiplied by this delta term. Now, the idea here is that if the response positively correlates with this point pattern, with the intensity, then they'll both go up and they'll both go down together. That makes eta a good predictor of Z, and therefore, when we optimize for this delta parameter, this will be a significant and positive linear coefficient, right? So that's exactly what we would see in this case, is that when we see high intensity, we also happen to see a high probability of presence, right? So we could, in this example, we would expect to see a very significant delta that is large, or that is positive. And if the opposite is true, if we were undersampling, if we were oversampling absences, is a way of thinking of it, then these would have a negative correlation, this eta and this z, and delta would then be significant negative. And so this is exactly that quantified value that I was alluding to. If delta is significant, that means you have preferential sampling. This is a way of formally testing it. Very handy. So here's the key interpretation. What's the mechanism at play here? Yeah, if we oversampled presences, which is in the Himalayan blackberry example, preferential sampling elevates Z near the presence-absence locations and lowers Z in areas away from it. So that's exactly what we wanted. We want that surface to be high along the path and low off the path. That's what preferential sampling allows. So if we don't have preferential sampling, our oversampling of presence makes it very high everywhere. But by adjusting preferential sampling, we kind of can imagine a ridge happening along this trail and kind of it dipping off away from the trail. And then we might have some local peaks, because we saw a blackberry bush off the trail over here. So it'd be low, it'd be low. It would be especially low here because we measured no blackberries. And then it would be high here because we did measure a blackberry. So that's the statistical mechanism at play here. And that's important because that's actually the mechanism we're going to use to fuse the data sets. Yeah.
Is there some guideline across studies and models for what is significant for delta?
Yeah, so that's going to be exactly, see, that's the trick. That's model selection. And model selection is kind of qualitative. So the way I would think about this is in the Bayesian paradigm, you would end up with a posterior for delta. And you would look at that posterior, and if mass accumulates near zero, then it might not be significant. In the Bayesian paradigm, you could also do a Bayes factor selection between the models that include preferential sampling and not. In the frequentist perspective, what you would do is you would simply look at the standard error estimates of this parameter, of the fitted parameter, so delta hat. And then you would run that confidence interval and see if zero lies in it. So that you'd run a hypothesis test is basically what that would be.
You can also get credible intervals.
Or credible intervals. Yeah, you could do credible intervals as well. Yeah, so that would be a more formalized way of just looking at the posterior and seeing where mass accumulates. If you look at where the posterior mass accumulates, you could also then create a confidence interval using that posterior mass, which is a Bayesian credible interval, and then see if zero lies within that. So these are all different types of model selection procedures, and they have their benefits and drawbacks. But hopefully, it'll be highly significant or highly insignificant. That would make your life really easy. Or sorry, if it was highly significant. If it's highly insignificant, then you have to decide if it's insignificant enough. So another thing, too, to mention, a big part of this paper was devoted to selling you on preferential sampling, saying that not only is this like a coherent method that has this really cool mechanism, but it's really good for improving your out-of-sample prediction. And so they took a real data set, they fit it with and without preferential sampling. They went deeper into it too. They started doing model selection on the covariates. And they basically showed that if preferential sampling is present, including this framework instead of just the latent Gaussian process, this Z, does very good things in helping you predict the true probability of present surface. Yeah.
So your example is very convincing because, in part because the process associated with the preferential sampling is correlated with the behavior of the species itself. Mm-hmm. But what if your preferential sampling has nothing to do with the thing that you're measuring?
Perfect. Yeah, I know exactly what you're talking about. That's exactly the selling point of this statistical method. So you're right, that knowing the ecology of the species means that, we should be using preferential sampling. My argument, though, is this. Even if you don't see a source for preferential sampling, it could still be within your data set, right?
Certainly it happens, but what if it's the opposite of where you think it should be because you have no data where there's an absence? Do you know what I mean?
Right, so you're always tied to the data you have. So for example, if this data set didn't have these points out here, you wouldn't be able to estimate these areas very well at all. So certainly you need data across your study area to be able to create a reasonable surface. But this method will be able to detect preferential sampling even if there isn't an obvious mechanism by which it arises, if that makes sense.
Well, but the assumption is that the preferential sampling does have to do with the presence or absence of the
Yes,
species.
yes,
So if the preferential sampling had with some other sort of reason that had nothing to do with where the plants were, but some other, like maybe the preferential sampling would be you happen to be sampling where there are lots of predators
sure,
eating all your whatever it is you're looking for.
yeah, perhaps our samples are correlated
What a
with
different
a,
kind of model.
yeah,
You could then model
Yeah.
them if you had predator-prey models or something.
right,
But if there was something that weren't related to the presence or absence of the species, then this wouldn't get at that kind of preference.
The
Right.
preferentials, it has to do more with the sampling scheme. I mean, it does have to, it will be affected by the data, but it has to do more with the sampling scheme that you end up using, right? Like if you're oversampling a particular type of region that has some specific characteristics, then preferential sampling, incorporating that term that Jacob is talking about, should be captured by that Gaussian process incorporating there. Or that's the idea, at least.
yeah. Ultimately, what we're looking for is, are the places we sampled correlated with their responses?
Yeah.
That's ultimately the question we're asking. And so we can get really creative about our interpretation of delta, but that's kind of irresponsible if because you're right, there could be a latent effect that we're measuring with delta. And so maybe it's not that your design was bad or that you had bad compliance by your field biologist. Maybe delta is just absorbing some latent effect.
Doing some of it, or
Trying to. Or it could even be, you could even have some weird, what's it called, heteroskedasticity or something. I don't know if that's the right one, but when this is actually correlated with one of the covariates, that could also be an issue. And you would have to run diagnostics to check those things. Okay, cool. So this, again, or actually I'll talk about it in a second too. Okay, so going back to this example, we have this mechanism that we can elevate the surface at areas that we did sample at if we have positive preferential sampling. If we go back to our data set, but now let's say that we have these extra red dots here, 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 and here. These are presence-only locations. So imagine you're doing your study, but then you heard at the water cooler that there's some really good berry picking spots at these locations, and that people have gone there and picked berries. And there surely are berry bushes there because they just don't die. And so you know there's confirmed presences there. How can we build that into this kriging model that we've built with preferential sampling? Now, keeping in mind that idea that delta elevates the surface at areas near we've sampled, Gelfand and Schroeder asked, can we leverage this framework to elevate that response surface near these newfound presence-only points? So our goal is we have, so far without, in this model with preferential sampling, we now have a surface that has a ridge along this path, and it kind of descends out here, has a local maximum here because we have a confirmed presence there. What if we also had little peaks around each of these confirmed sightings? What if we could do that, where we have that peak here, and then it slopes off, but we have some points that are high over here? And to do that, they leveraged this idea of preferential sampling. They basically just built in this point process model for the presence-only data, the red ones. So that's what this represents. This is the point process model for the realization of the red points. And then this is the point process model for the realization of the gray and black points, the presence-absence data. And then we now have two ADAs. We have a presence-only and a presence-absence ADA, and both of those terms go into the mean structure of this response surface. So that means that, I should talk about one thing we do here too. We want to make sure that this surface is heightened at those red points. So let's make sure that delta PO is positive, right? That if it was negative, then we'd actually be artificially lowering that surface. And so to deal with that, a nice way of doing that is to just put a positively constrained prior on that particular parameter. They suggested truncated Gaussian. So that's what I show here. So this idea is that the main takeaway is that this delta PO will be positive, and this will add those peaks at the red points that we're looking for, and this will add that nice ridge along the pathway that we're looking for. Cool. This is the final model that they prescribed for dealing with the data fusion problem. We've now successfully built a model that takes into account both the presence-absence and the presence-only data. Here's where I talk about some model selection. We kind of got into this earlier, but I just went through that easiest model. Posterior mass accumulating near zero, drop the parameter. So you might build a decision based on a Bayesian interval, a credible interval on the posterior mass for each of these parameters. So that's what I'll assume for my model selection method. So what are the kind of the implications of that thing? Well, if delta PA is insignificant, we don't really have preferential sampling, right? And so then we don't have to model lambda PA at all. We could drop this entire equation from the model. And so that might help, especially if we're doing complicated simulations and with lots of parameters. Also, are the nugget effects significant in any of these? That's kind of like the measurement error. We could drop those if we wanted to. Of course, we could do covariate selection on all these covariates. Or sorry, no, that's what that was. Here I'm talking about are the covariance function parameters. So this is like that phi. Is that significant in these values? Because if not, we might not have spatial dependence, and we might need to use a different model. And then we could do covariate model selection on all these covariates here. So there's lots of nested models, and they actually explored quite a few in the paper. This is the most general, so this is really all we're talking about. So the biggest issue here is that we assume that all the presence-only data was sampled because it's a point pattern model. Now, we assume the same thing for presence-absence data, but all of the presence-absence data was sampled. So that assumption doesn't really have an issue. If all the presence-only data was sampled, what that means is that we actually censused the entire area D, which is not the case. We just heard through the grapevine that there's some good berry picking locations. So what that does is it elevates that Z near those presence-only, near those red points, but it also decreases Z at places away from it. That's a problem, right? Because, I mean, if you assumed that you had all the presence-only data, it would make sense to lower that surface at places away from the points that you gathered. But because we didn't actually gather all of them, this is actually not good for us. So we can do that by what's called degrading this intensity for the presence-only data. That's developed by Diggle et al. In 2010. Really what that does is it kind of creates a little boundary around each of those presence-only points and says, okay, we're only modeling this intensity at that little neighborhood. You only have influence there. You don't have influence anywhere else. But that creates some weird discontinuities in the resulting surface, which isn't ideal. And also this degraded likelihood, the likelihood that arises from this, it includes this integral. We're integrating over an uncountable, this domain that's a random domain that is really impossible to integrate over. And so to fix that, you can model intensity at the areal level, which isn't ideal. So maybe there's a more elegant solution to that. Here's some extensions. So that's like the main issue to fix this model. Here's some extensions we could use for this kind of modeling technique. We could build in abundance modeling. So now instead of mapping to 0, 1 probability of presence, maybe we're mapping to a surface that describes what we expect the number of a certain event to be at any given point. We could also do joint models of multiple species, which is as complicated as it sounds. And also spatiotemporal modeling and animal movement models, which are both time dependent. Those are even more complicated, I think. I don't know, these are all really tough. These are ideas that were cited in the paper as extensions. And this is one that I identified myself that I'm really interested in. Extending this presence model to an occupancy model. And the only difference there is that you're not only modeling whether or not the species is there, you're also not assuming you have perfect detection. So you're going to have to model detection given presence along with presence. So that's an extra component to build in. Under the Bayesian paradigm, it'd probably be best because we have a lot of moving parts now, but we then need suitable priors and samplers. which isn't really straightforward. But this is an open area of research that they didn't say in the paper, and it could be part of my PhD work, possibly. Any questions?
Let's thank Jacob. Anybody has a relatively quick question? I have one.
Yeah.
Go back 4 slides where you were talking about the whole model structure there. So are the points in the presence only the same points you used to fit the presence absence?
No, these are totally different sets. So the only models used to fit this regression is the red points, the presence only. And the only data used to fit this presence absence are the gray and the black points. So these are disjoint data sets.
So you have some sort of latent process going there because the term eta is shared and it's evaluated at S. So you're needing to do some sort of, so here?
Mm-hmm.
Oh, sorry, here. So this term is both here, and so you have S here and S here, right?
Yeah.
And because you're only fitting these with the presence only points, and you're only fitting these with the presence absence points, how do you go about that?
Ah, right.
That was your sort of your point about letting lambda depend on S all.
Right.
Yeah.
I'm not exactly sure.
Yeah.
I mean, the appendices for the model fitting details were rough to wade through.
Yeah.
So I'm not sure.
You just do some prediction, you sample those points.
Okay.
So you sort of fill in the gaps for either model, depending on what you have.
Okay.
Okay.
Yeah, Kat?
So online platforms like iNaturalist or eBird or something, they have mostly, it's not going to places that you expect to see them, it's going to easy locations, urban locations that are over-exampled. If you use the same exact model for that, especially if it's combined with some ecologist data where there's true presence absence, then you have this community scientists have all the presence only, and even though it's not, it's just
Absolutely.
oversampled there.
Absolutely. That is.
So that's the same exact question. So that's what you need to do with this data.
Yep. This is the perfect framework for that. So again, just because you can't identify, because it's not obvious there, it depends on the species, whether or not urban areas are better for the species or not. And maybe you can't claim to know that, whether it's better or not. And maybe it's spatially dependent. And maybe it's dependent on some covariates that might be absorbed in these equations. So yeah, the takeaway is just because you can't identify a source of preferential sampling doesn't mean that there doesn't exist one. So ideally, I would advocate for fitting this model and then doing model selection. Fit the general model with everything in it and then do model selection. Just assume that everything's significant to begin with. Yeah.
One of the things that bothers me is that you're potentially having a whole lot of parameters to fit just a couple of data points, like particularly the presence-only data.
Right.
If you really have several betas in that model,
Oh, yeah.
and you only got 5 points,
Yeah.
and you've got 6 betas, then you can fit them perfectly. Something's wrong, basically.
Yeah. So surely, yeah, those regression equations are constrained a lot by the data that you actually have, this presence only.
You
So
have to build a somewhat separate model
yeah,
on that, probably assuming maybe almost constant or something.
or to make your life easy. I mean,
Yeah.
I don't know, I've seen a couple of these data sets, and typically they're pretty big.
Presence only is more abundant, right?
Yeah, presence only is way more abundant. The idea is like
I
with
guess
presence
I'm
only.
used to ones that aren't that good.
Right.
You can get a couple hundred observations, you're doing great in
Yeah.
some situations.
With presence only, you're going to the library, you're talking to ladies at church. You can find all kinds, as long as they're credible and the locations that they say that the species is at, that sample that they took was recently, temporally enough that it's still the case. So with Himalayan blackberry, those things don't die. So it's going to still be there if they picked blackberries there last year. As long as you can meet those two assumptions, that it's just a rigorous enough point, you can collect that presence-only point. And so typically finding presence-only data isn't a tough problem.
Right. Wrap it up.
Okay.
All right, let's thank Jacob again, and if you want to stay and ask some questions.
Thank you.
So you talked
Let's go
about
ahead.
like the location and intensity stuff, like location of tree and diameter of the tree.
Yeah.
Is this able to do that extra dimensional stuff as well?
So you might,
I mean, other than it being nice without working on the surface at that point.
So one thing you might do is you might take those marks, those covariates that you measured, and you might build them into this presence-only structure here as a linear covariate. Or, I mean, you could get fancy with this too. You could put squared terms in here. I mean, it then just becomes a multiple regression problem. But yeah, that's where you'd build it in.
You could even do some nonlinear things if you have enough data.
Yeah.
Non-parametric, just curve fitting.
Right.
things like that.
Cool. Right. Any more questions, I guess? No?